My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, and the YouTube channel, Kumar Das, I'd like to welcome you all to our International Physics webinar, and I'm happy to share with you all that today is our 6th International Physics webinar. So good evening to all. I hope you are well and safe from Corona pandemic. So all we know that we are living in a Corona pandemic situation. So we cannot continue our normal academic program inside the campus due to the Corona pandemic. So we have to start our online program. I think you have already come to know that our department have already started its online program, including online classes and online international physics webinar, and we have already successfully completed our 66 international physics webinar, and today it's our 67. So we're trying to adjust with this new normal situation, and today it's a very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, Physics, University of Calcutta, India, in particle physics and high energy physics. And we have with us here today Dr. Abhijit Bhattacharyya sir, Professor, Department of Physics, University of Kolkata, Kolkata, India, and he has already connected with us, and I'd like to welcome our speaker. So good evening, sir, and welcome to our
good evening. Very good evening.
And thanks again. So this is your second webinar in our International Physics webinar, and we are very happy to host you. And we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So for those who are new, I'd like to inform that we have divided our webinar into 3 parts. First of all, we would like to introduce our speaker with all of you, though you have already know our speaker very well, as this is his second lecture in our International Physics webinar. And then our speaker will deliver his speech, and at the end we have a discussion time. In that time, anybody can join with us. So I think you have already come to know the title of our today's International Physics webinar, and title is the Thermodynamics of Strongly Interacting Matter. And our speaker is Dr. Abhijit Bhattacharyya sir. He is currently working as a professor, Department of Physics, University of Kolkata, West Bengal, India. And if we see his academic and professional background, we can see he has completed his bachelor degree from Presidency College, India, and his MSc degree from Indian Institute of Technology, Kanpur, IIT Kanpur, and his PhD from Bose Institute, Kolkata, and postdoctor Alexander von Humboldt Fellow from Frankfurt, and visiting scientist Professor Germany, and member Germany, Italy, France, Japan, Poland, and other countries also, Switzerland, Hungary. So member of the collaboration board, compressed baryonic matter, GCI Germany, research interest, ultra relativistic heavy ion collision, phase transition in strongly interacting matter, neutron star, and others. So thanks all for all of your patience. Now it's our time to go to our speaker. So, sir, thanks again, and welcome to our International Physics webinar. It's your time. You can start your session, sir.
Okay. So let me first say good evening to all of you, and thank you, Professor Pretam Das, for giving me this opportunity second time. Can you see the whole screen, Pretam?
We can see it.
Yes. Okay. So basically what I'll do today, I'll basically heat and compress my last talk. Basically what I'll do in the last talk, I discussed the basic aspects of particle physics. Today, I'll basically discuss the thermodynamic aspects of particle physics. What I will do is that I will just take all those particles in a thermal medium. I'll try to be as general as possible in this talk, and if you have any question, as Pretam said, you can ask me anytime you want. So let me just proceed. This is the panorama of particle physics. As I say, that basically everything which we see around us are made up of these particles. Let me say what are these. If you can see my cursor, in these purple colors, we have these 6 quarks, 6 types of quarks. They have nice names: up, down, string, charm, bottom, top. These 6 types of quarks, they have fractional charges, plus 2/3 in upper row, minus 1/3 in the lower row. And then we have so-called leptons, electron, muon, and tauon, and with each of them there is one neutrino associated with. Electron neutrino, muon neutrino, and tau neutrino. So basically, these are all fermions, and we have their antiparticles. So then we have these 12 fermions, and then there are antiparticles of these fermions. And then on the right side, we have these bosons, which are basically, we say gauge bosons. They are carriers of field. We know that there are 4 types of forces in nature, namely electromagnetic force, gravity, strong interaction and weak interaction. This photon is considered to be the mediator of the electromagnetic force. The W and Z bosons, they are considered to be the basically the mediator of weak force or electric force. The gluon is the mediator of the strong force, and we are yet to be able to quantize the gravity, so we do not have any boson here. And this in yellow is the newest addition, of which I have talked in quite an amount of detail last time. This is the Higgs boson. So let's proceed further. My job in this talk will be basically to put this whole thing in a medium in the sense at a finite temperature, at a finite density, and what does these two terms mean in the context of particle physics. I'll of course try to explain to you. Okay, now it's true that everything is made up of, going back again, everything is made up of these quarks, but we don't see them. What we see in nature are some particles called hadrons. The name hadron may or may not be familiar with you, but what may be familiar with you is their examples, which are the examples which are protons and neutrons, etc. These particles are called hadrons. Hadrons are particles which are made up of quarks. So hadrons are made up of basically these 6 types of quarks. So, but if the hadrons are made up of quarks, fine, we see hadrons, that's also fine. But why don't we see quarks? Why do we see hadrons? We see quarks, we do not see quarks, we see hadrons, that is protons and neutrons, simply because of the fact that these quarks are always confined inside the hadrons. Look at this figure. There are 2 types of models to explain this, basically a phenomenon called confinement, why these quarks are always inside hadrons. These people say that there is a bag here and there is a back pressure. The back pressure is such that the quarks which are inside, which are shown in red, blue, and green, cannot escape this bag. And as a result, they are always confined. That's a modeling of a fact that the quarks are always inside the hadron. So this is my hadron, and inside we have this quark because due to confinement, they are always inside due to back pressure. There's another model called flux string model, which says that there is a string associated with 2 quarks. And if you try to take them apart, then the string tension increases. The string tension is such that if they are close enough, there is almost no string tension. That's a phenomenon which is called asymptotic freedom. And if you try to take them apart, then there is, at one point of time, the string tension becomes infinite. As a result, you cannot take them apart after a certain distance, so they are confined. So we see only protons and neutrons. Our goal in this talk will be to show that under certain conditions of temperature and density, we can bring these quarks out of this bag or break this string up to a certain extent so that the spatial dimension of these quarks and gluons will be a little bit more than the typical size of a hadron. Typical size of a hadron is of the order of a Fermi, which is 10 to the power minus 15 meter. So if I heat it or compress a hadronic system, then my claim at this level is that I can have a medium on which I'll have quarks and gluons, and the medium size of the medium is more than the size of the hadron, that is more than 1 Fermi. There will be few Fermi. So let's do that, whatever I was claiming. Let's just heat or compress it. Come to this middle thing, in which these small things are my hadrons, protons, or neutrons. And inside it, if you can see, you will find that there are these tiny dots, colored dots, those are quarks. Now, if you heat them, just boil them, these tiny small bags or small spheres will blow. I mean, the size will increase. So at one point of time, one of these bag or one of these spheres will overlap with the next one or nearest ones. So in this whole volume, when they will overlap, there will not be any boundary. I will not be able to say that this quark belongs to this hadron or this hadron. So I have a medium like this, in which I'll have only quarks there. Okay, and these quarks interact via gluon. Don't forget that, which I've said in my first transparency. I can achieve the same thing by compression. That I compress it so hard that they become very close to each other, so that they overlap. So these quarks inside, they lose their identity. This red point that you see, there's a quark belonging to this hadron. There is another red point or yellow point you see belonging to this hadron. And I don't know, if I compress it, they overlap, all of them overlap. I won't be able to say whether this red dot belongs to this sphere or this sphere or this sphere. I'll have a medium like this. So this medium I can achieve two ways, either by heating or by compression. And that medium is called quark-gluon plasma. Why this is important? I'll show you here. I have written it, but I'll show you in details here. There are cosmological and astrophysical relevance of whatever I claim here, or whatever situation I depict here. Now, this is something called a phase diagram. So if I go back, then here the degrees of freedom, degrees, the word, if you are not familiar to the word degrees of freedom, it means that these are the particles by which we describe a system. Over here or over here, these were hadrons, means protons, neutrons, and over here, these are quarks. There is no hadron here. The overlapping, I mean, those all them overlap. I have an extended medium of quarks and gluons. So the degrees of freedoms here are quarks and gluons, and the degrees of freedom here are basically hadrons. So this is something called a phase diagram, in which I plot here temperature Tc. What does that mean? I'll tell you. This is called chemical potential. If you do not know chemical potential, forget it. You may call it a density, some kind of. On one side, you will have hadron. On another side, you have quark. So on the hadron side, you have this situation. On quark side, you have this situation. Tc is called the critical temperature at which this hadronic medium, or the medium comprised of protons and neutrons, get converted to the medium of quarks and gluons. So if you increase that temperature, then, or if you increase the density, it will need less temperature. So basically, what you have this diagram, that at this point, at very high density, even at zero temperature, the matter will get converted to quark medium, go from here to here. At this, over somewhere here, the density is somewhat less, so it will need more temperature. Over here, it will even more temperature when density is zero. Or the temperature is so high that at density zero, it gets converted. So this is a boundary line. On one side, we have hadron. On one side, we have quark. If you want to know what is this typical temperature in your known units, you just multiply it by 10 to the 10. So it is about 10 to the 11 degree Kelvin. And if you want to know what is typically this density is, it's extremely high. Over here, it is about 10 to the power 15 grams per centimeter cube. So 10 to the 15 times that of water. The density of water is 1 gram per centimeter cube. Fine, let me go further. I was talking about the relevance. And this is one thing. This is called the Big Bang picture that I have presented to you. At about 15 billion years back, there was a bang. We believe that there was a bang and our universe was created. Okay? So the forces were unified up to about 10 to the minus 35 seconds. Then there was an inflationary expansion. After the creation, the universe expanded. Then there was an inflationary epoch, we call it. Inflationary epoch means, just give me a second. Inflationary epoch means the universe accelerated, the expansion was accelerated. So you see the size of the universe accelerated in the region very fast. It's called inflationary expansion. Our universe keeps on expanding even now. Then we come from here, and if we draw a vertical line, Then on this side we have gluons, electrons, quarks, electron, quarks, gluons, W boson, photon, etc. And on the right side, there are no more quarks. Nucleons form. Nucleons means protons and neutrons, and these quarks get confined inside these protons and neutrons. And basically, as the temperature goes down, then you do not have energy for the quarks to be free, and they get confined inside these protons and neutrons. After some, that is about 10 to the minus 5 seconds after the Big Bang. That is about 10 microseconds. If you talk in terms of temperature, this is 150 million electron volt. If you're not familiar with this unit, then multiply it by 10 to the power 10. So it's about 10 to the 11 to 10 to the power 12 degree Kelvin. Now, then the university cooled. After about this time, the atoms formed. So after 10 to the 9 years, the stars are born, and we are here today at about 15 billion years. That the temperature is 0.7 milli-electron volt, which is in our known units about 2.7 Kelvin, which is mean minus 270 degree of degree centigrade. That's the average temperature of our universe. So it's pretty cold. So it started from an infinite temperature, and in 15 billion years, it has expanded and expanded, still expanding, and then it's and it has cool as it expanded. It's cooled naturally from thermodynamic relations. One can say that, and as it cooled, it has reached a temperature which is extremely cold. So our relevance, the thing that we are going to discuss is somewhere here, that we started with an epoch, we started with a history where we had quarks and gluons and got converted to protons and neutrons. And then, of course, after that, atoms were formed, molecules were formed, complicated molecules were formed, then we see everything around us which were formed. Now, to know the history, to know the expansion, and also to know the fate of the universe, we must know what it was, what was the composition, at what point of time the universe had, so that we can completely determine the evolution of the universe. So that is the relevance, that how this thermodynamics was at such a temperature, as the 1 degree of freedom got converted to the other degree of freedom, what was the situation. So to understand the transition, what is called the phase transition, is required. So that's the cosmological scenario. There's astrophysical scenario. You remember, this is just a temperature case. I have not talked anything about density. I'll talk about the density, I mean changing the degrees of freedom by density now. That's an astrophysical scenario. We know these stars, these known stars around, they are stable because of two things. One is inward gravity, that is the self-gravity of the star, and one is the outward pressure because of the thermal burning. Okay. Now, we have this stellar evolution. What happens basically, the star burns, and as a result, we give this thermal pressure. How it burns is different envelope. From the center, first the hydrogen burns, then the helium burns, carbon burns, oxygen burns, up to iron, because iron is the stable most nuclei. As this reaches iron, there is no further burning. The star dies, all the fuels are burnt out. There is no outward thermal pressure anymore. The only pressure is the gravity, inward gravity, and the star starts to collapse. A situation which is called supernova. When all the fuels are burnt out, the star collapses. And what is formed is a compact object is formed. How that is formed? Once again, that is formed because it's stable against gravity and Fermi degeneracy pressure. What is that? The fermions, which are electrons, protons, neutrons, all are fermions. So one object is formed, what is called white dwarf, that is composed mainly of electrons. So you have electrons gives a pressure outward, and there is gravity inward, so that is stable. Or you have neutron star, which is made mainly of neutrons. So basically, the neutrons give an outward pressure. It's called Fermi degeneracy pressure. I will not go into detail of that. And the inward pressure is gravity. Now, Apart from that, if the star is very big, it doesn't have a Fermi degeneracy pressure, the star is no more stable and collapses to a singularity called black hole, which I will not discuss today. Now, why these are called compact? Here I have given you some example of masses of in terms of solar mass. For example, Sun has a mass of typical, Sun is just one. I mean, I'm expressing it in terms of solar mass. Earth is 10 to the minus 6 times of Sun. Jupiter is minus 10 to the 3, 10 to the minus 3. White dwarf, as I said in the previous slide here, white dwarf is typically solar mass. So is neutron star. Now, look at the sizes. So Earth is about 6,000, Jupiter 10 to the 4 or 10 to the 5, Sun is about 10 to the 6 kilometers. This I'm talking about. The white dwarf is 5,400 and neutron star is only 10 kilometers. So what does that differ? That makes the average density different. In grams per centimeter cube, where the density of Earth is 5.5, that of white dwarf is 3 into 10 to the 6. That of neutron star is 5 into 10 to the 14 grams per centimeter. So we have a situation in the sky where we have these compact objects which are extremely dense. So if I go back few slides, if you allow me, then we have this situation of high density here where the situation is extremely dense and such a density makes things overlap. Now, so we expect to have a degree or things which are made where the degrees of freedom are quarks and gluons. Okay, so let's go further. These are typical, a nice picture of neutron star. This is a neutron star where this is called the surface, which is basically atmosphere. Then we have an envelope. Then we have something called crust. Then we have outer core, and there is inner core. And this inner core contains our things of interest, where the density can go as high as 10 to the 15 grams per centimeter cube. As I said in the previous reference, the average density is about 10 to the 14, but at the center it can go as 10 to the 15 grams per centimeter cube. It will be much more visible, easier to conceive if I give you a two-dimensional picture. This is basically surface where you have different nuclei, electrons. Then you have neutron-rich nuclei. Then you have superfluid neutrons, some protons and electrons. The whole thing has to be charge neutral. So the number of protons and number of neutrons have to be equal. And at the center, you have high density where you expect to have quarks and gluons. So I hope by now I have been able to convince you why should I look into this particle physics at high temperature and density, because these have this cosmological and astrophysical significances. Cosmological, where the temperature is high, and astrophysical, where the density is extremely high. Okay, now let's proceed. These are objects far from us. We can touch them. Of course, we can get some signal. We can recreate this situation of changing the degrees of freedom from hadrons to quarks or quarks to hadrons in the laboratory, in very few laboratories, but certainly we can do that. How do we do it? We do that by collisions of heavy ions. These are done in certain laboratories. I'll talk about those. So this is basically a more detailed picture where we collide two nuclei, say lead, heavy nuclei. Why I have not drawn spheres? Why I have drawn it more like a pancake? Because their velocity is extremely high, relativistic velocities. At that velocity, this length is contracted. If you know about the Lorentz contraction, so from a rest frame, they look like these pancakes. So when they come together, they collide here, they produce a region of very high temperature and density. Let me mention here, if the energy is very high, then you have more temperature compared to density. If the energy is low, you have more density compared to temperature. So don't think that low energy is always negligible. You can throw them out. Low energy is high density, low temperature, and high energy is high temperature, low density. So depending on what physics you want to discuss, you will be in that domain. So they form such a thing, hot and dense medium. They expand. As they expand, they cool, and they cool, they become again go back to hadrons, that is protons and neutrons. So we start with hadron, we go back to hadron. In the medium somewhere, maybe we have produced a domain. If you take a snapshot of time, then we have produced in certain small time scale a matter made up of quarks and gluons. In the detector, we don't get these quarks and gluons. We get hadrons, protons, neutrons, pions, etc. But they carry certain properties, their momentum, their energy, and a lot of other things, which should be able to tell me that when they have generated. There are other particles like electrons or photons, okay, which carry certain information that whether such a domain of quarks and gluons have been formed. So we look for it. So we can recreate this situation which is available naturally in astrophysics and cosmology in our laboratory. So these are some of the such experiments. I have listed them. Okay, first one was in Bevelak. I listed them somewhat historically. This was in LBNL Berkeley. They were operative during 1984 to 1993. I mean, this is the name of the accelerator. This is the name of the experiments, different collaborations of experiments. Then there was alternative gradient synchrotron AGS at Brookhaven, National Laboratory, Brookhaven, operative during this period. So we are increasing in energy. You can see it. If you see this, we get this 2 GeV per nucleon, is 14.5 to 11.5 and 11.5 GeV per nucleon. The projectiles we used were different. You can see the nuclei here, and these are the name of the collaborations. Then we had superproton synchrotron, gave a lot of data to us from CERN Geneva. Then we have cis-18, Schwerinian ion, I mean heavy ion, it's in German language. So this we have this 1992 still running. It's at low energy. It's very important. This is a low energy thing. And this is important, I'll come back to. We have RHIC, relativistic heavy ion collider at Brookhaven, running from 2000, gave us probably the first indication that we have quark-gluon plasma, 200 GeV per nucleon. And these are the collaborations we have. Of course, all of you know LHC at CERN Geneva operating. And these are coming up. This CIS-300, okay, and at GSI Darmstadt. And this is not, the work hasn't started yet. It is in Jubna. In fact, the CIS-300 is also not started yet. This is the work has started, just the data is expected at 2025 or 26, something like that. This is at Darmstadt. And there is a collaboration called compressed periodic matter. This will come later. So there are two types of experiments. One are called colliders, where the people are circulated in a ring at high energy and they collide. And then there are fixed target experiment where you have a fixed target and the beam hits. Now we come back to the same phase diagram, because we have learned from the previous diagram to here, we have learned a certain thing. This is the same phase diagram, and I have plotted it with the density in terms of nuclear density. Nuclear density is 10 to the 14 grams per centimeter cube. So here we can up to 5 to 20 nuclear density. After that, you get quark-gluon plasma. Beyond that, you have hadronic matter. And this is the early universe situation. This is the neutron stars high density. And these are different experiments. These are the regions of phase diagram which different experiments they survey. So our knowledge is enriched with which experiment survey which region of the phase diagram. So that we can now tell. This is basically LHC is very high energy, so more towards temperature, high temperature. This is the new experiments where they want to study high density region, so they are of low energy. Let's proceed to the case. Now, for the next few transparencies, just 7 to 8 transparencies, I would like to tell you that what we theorists calculate at finite temperature and finite density, high temperature density, just a few. Then I'll go more to the experimental situation, how things are calculated. We calculate certain thing called order parameter. Order parameter is something which goes from, this is low temperature domain, that is at hadrons, to the quarks. And if they do go this smoothly, then we say there is a crossover, there is no phase transition. Okay, what is phase transition? And if at very high density you have a gap, this is not something of your calculational mistake. This is something you can never achieve in your calculation. So you have to see a first order phase transition. A first order phase transition is typical example when water is converted to ice. Okay, and a continuous phase transition, very crudely, is when ferromagnet is converted to paramagnet or vice versa. So our phase transition line is not that simple. We have a dot here. At high density, we have a first order phase transition. At low density, we have a smooth crossover. If I may go back, this is a smooth crossover. And if I go here at finite density, there is a gap which you can never achieve. Okay, that's the first order phase transition. What else we calculate? We calculate pressure. Pressure in terms of Stefan-Boltzmann pressure. I've divided it. Stefan-Boltzmann pressure is nothing but free gases of quarks and gluons. So we see that from low, when the quarks and gluons are bound, the pressure increases, and should go to 1 at very high temperature where quarks and gluons are free. At low temperature, they are bound. We get that indication. We calculate something which is called energy minus 3 times pressure. So if it's a perfect gas at it, this should be 1. This should be 0 in minus 3p. You can see at high temperature it's going to 0. And somewhere, you see I've plotted all these T versus TC. TC is the temperature at which hadron matter goes to quark matter. So at TC1 is maximum, then it goes there. Then we calculate specific heat. There's the energy required to increase the temperature by 1 unit. We see a peak at this. Okay. We calculate pressure energy density. This is the indication that there is a transition. This small dip. I just want to show you what we calculate. This is the velocity of sound, is the same thing. It's just the velocity of sound in the medium. Experimentally, none of these things are calculated. They calculate just number of particles in their detector. So they calculate number of particles n. You can calculate the average. This difference is basically gives you the standard deviation. In some language of statistics, this is called skewness and this is called kurtosis. These are things which are measured in experiments. In experiments, they also measure the spectra of different particles. These are the spectrums of dielectrons and photons. These are real data. These two plots are real data coming to the detector. The number of particles coming per unit mass and in certain other things to the detector as a function of their invariant mass. How do they look like? These are real experimental data I want to show. For the rest of my talk, I will discuss how and where these things are measured. I will not leave any mathematics anymore. I will not discuss any mathematics anymore, and I'll discuss what are the things which are discussed in the, how things are measured and where they are measured. Of course, you know all of this. I discussed in my previous lecture also. The most popular thing is in the Large Hadron Collider. It's called a Modern Marvel, which is in Geneva. It is spread over 2 countries. This is the ring, 27-kilometer ring. Okay, over here is Switzerland, and this is France. Okay, and you have a tunnel of 27-kilometer circumference, passes through 2 countries, and there are 4 large experimental groups. What it does, it basically collides proton with proton, and it's always proton with lead and lead with lead. Okay, basically protons, basically particles with large nuclei and large nuclei with large nuclei. Maybe so to say. This is how it is done in CERN. Okay, the protons are obtained by stripping electrons. You know that if I take one electron from hydrogen, it's just a proton. The nucleus of the hydrogen is just proton. So strip it off, ingest it to the PS booster over here, proton synchrotron booster. You take that hydrogen, it boosts and accelerates at 1.4 GeV and feeds to the proton synchrotron. From proton synchrotron, it goes to the superproton synchrotron, which was there previously, which then feeds it to the, it accelerates about 450 GeV and then it switches to the LHC. LHC, this is accelerated. The ions more or less are first to that what is called low energy ion ring, which is called Vl, and then if you want proton-proton or proton-ion, whatever, you just collide. That's what exactly done in sun. Now, LHC is basically even colder than the outer space. You have superconducting electromagnets to bend them. About 8.3 Tesla of magnetic field, which is more than 100,000 times more powerful than the Earth's magnetic field. If you want to make the particle rotate over it, you have to bend this particle. To bend this particle, you need magnetic field. And it's about 100,000 times more powerful than the Earth's magnetic field. It needs this much of ampere of current. Think of it, how much it is. 11,080 amperes current to produce this field. And it generates heat, so you have to cool it, and superconductivity comes to rescue. This is called niobium titanium wires which are used. 1,232 dipole magnets are used, and 392 quadrupole magnets are used. Now, superconductor works at a very low temperature, and this is the temperature at which the LHC magnets are used, minus 271.3 degree Kelvin, or the outer space, as I said, about minus 270 degree Kelvin. So it needs about 40 megawatt of electricity, 10 times more than a locomotive. And 120 tons of helium keep the magnets at this temperature. LHC is emptier than the interstellar space. I mean, if you have high pressure inside, then the particles will simply not move. Okay, so you need a very low pressure. You need 10 to the minus 6 times, minus 6 millibar of pressure to basically to cryogenically cool magnets. So otherwise, the whole effort will be lost. Now you'll see vacuum systems are fitted with 170 Baird-Alpert ionization gauges and 184 Pirani gauges to maintain this vacuum. So it is colder than outer space, it is emptier than interstellar space. Now what happens? These particles, they collide, or ions, they collide, they produce new particles. These new particles go to the detector. So we need a very good electronics to detect them. Okay, there are different detectors. Large number of plethora of particles come and jump into the detectors, and detectors, they detect them. All this detail. So very fast and very efficient detectors are required to detect all these things. Now, the question is, and of course, there is another thing which is required, which is cutting-edge computing. This cutting-edge computing is required because you have a plethora of data, and those particles will jump into it. So you have to detect them. There are a huge number of particles. Those huge number of particles will basically need huge number of space. So they need cutting-edge computing. So LHC is basically underground, so it's 100 meters below the surface, and there are 4 experiments which are taking part here. The dedicated experiment for quark-gluon plasma is ALICE, which is a large ion collider experiment. Apart from that, the quark-gluon plasma experiments will also get data from ATLAS and CMS. LHCb is dedicated from something else. CMS and ATLAS are not primarily meant for the heavy ion experiments or quark-gluon plasma experiments, but we'll have some data from here also. This is the ALICE detector. This is a typical size of a human being. So you can see the huge thing which is going on there. And this is what is called a muon detector, the different part, the TPC, different parts of the detector. This is the part where the gamma and pi 0 will be detected. And this is what is called photomultiplier detectors, where the photon multiplicity will be detected. This is a huge detector which is dedicated for the study of quark-gluon plasma. So that's LHC. Now, what is after LHC? What will be? This LHC is mainly dedicated to study the high temperature part of the phase diagram. the low density part, closer to early universe scenario. To look into the high density part, the astrophysical scenario, another facility is being built up. I mentioned it towards the beginning of the talk that this is the work going on at Darmstadt, south of Frankfurt in Germany. As you see here, we expect data from 2025, 2026, somewhere like that. Here we'll have an extremely high density and extremely low temperature. So the energy should be low. That's very challenging. Low energy is not easy. Low energy is challenging because as the energy becomes lower, the statistics, the number of particles coming to the detector decreases, and you need very high luminosity. To produce very high luminosity of the beams is an extremely challenging job. So it's maybe even tougher. So many countries are involved in it, and will try to find out the first order transition range in this. So coming back to the end of my talk, we'll basically time and again we'll basically study this diagram. This is the third time I'm showing this phase diagram. So we have got a lot of data in this region from LHC at high temperature and low density, and we are desperately trying to extract this region, which is even tougher. So the Rick has already told us that we could produce a quark gluon matter, for sure, and now we are studying this region through LHC, and from 2025 we expect to get data from this region to neutron star region. So at the same time, we'll have access to the early universe scenario, and in the neutron star scenario, the cosmological scenario and the astrophysical scenario recreated at our universe. So that's all I have to discuss with you. Thank you very much for your kind attention. Pretam.
Thank you, sir, for your nice presentation, sir. So I think the students have learned a lot of things. So if you allow, sir, we can start our discussion session. We have got some questions, sir. So I can start read it out. So the first question, sir, both lepton and quarks are fundamental particles, but why the quark doesn't exist naturally?
I'll just change the question a little bit. It's not that quark doesn't exist naturally. We do not see free quarks. Quarks are always inside protons, neutrons, or called hadrons. Because quarks are strongly interacting. Leptons are not. So leptons are charged electrons are interacted by electromagnetic field. So which is much, much weaker than strong interaction. And leptons, so they are free. I mean, quarks interact by a strong interaction, so you cannot take two quarks after a certain distance. The interaction is so strong, you cannot take them after a certain distance. So to put it very crudely, that as you increase the distance, the potential increases. It's just inverse of Coulomb force. And Coulomb, as you take them apart, the force decreases. So you cannot take them after a certain distance.
Thank you, sir, for your answer. So we have another. This is not a question, just request. Please discussed on recent Nobel Prize topic.
I'm not an expert.
So
I'm not an expert in this. I should not comment. Maybe you should ask some expert to comment on it. Well, I did and I read it, but I should not do it. I mean, I just know that this is some work on black hole. No, I should not. I'm not a qualified person.
Yeah. Okay, sir. So thank you. So we should conclude that as there is no more question. So thanks again, sir, for your wonderful lecture, sir. I think the students have learned a lot of things about particle physics and high energy physics from your lecture. And we actually feel very happy that you have given two lectures in our international physics webinar. So we are very grateful to you for that. So hopefully in near future, if you have a free time, we will arrange another webinar with you, sir. So thanks again, sir. And in near future, after the COVID, we'll definitely visit our university for face-to-face program.
Bye.
Yeah, thank you, sir. Bye for today.